In the previous lecture, we have discussed in detail the carrier concentration and Fermi level in N-type semiconductor. And today, the same problem is to be dealt for P-type semiconductor. Okay. So you can see, I have shown here in this figure the energy level diagram for the P-type semiconductor. Okay. Actually, this energy level diagram for a P-type semiconductor, as you can see in this figure, uh, this will be utilized to find the concentration of holes in valence band in this P-type of semiconductor and its Fermi level. Okay. Actually, this problem of calculation of carrier concentration Fermi level for P-type semiconductor can be treated in the same way as that you have treated the problem for the same subject for N-type semiconductor. Okay. So using the ideas utilized in the previous lecture, we will see this problem and we will calculate the carrier concentration and Fermi level for the P-type semiconductor. Okay. You know, a P-type semiconductor is formed when a trivalent impurity is actually doped in a pure semiconductor of germanium or silicon. And this trivalent impurity, you know, are also known as acceptor impurities. And these acceptor impurity atoms occupy the acceptor levels, which I have marked here by this dotted line, and its energy is equal to EA. So at 0 Kelvin temperature, all the impurity atoms lie in this acceptor level, which I have marked in this figure by this dotted line. And at 0 Kelvin temperature, when you take T is equal to 0 K, then there is no thermal agitation, okay, no covalent bond in valence bands are broken, and in acceptor level all the impurity atoms are in unionized state. It means they do not gain electron from the covalent breaking of covalent bond, because at this temperature there is no breaking of the covalent bond. So all the atoms in acceptor level are unionized. Okay. But whenever there is a temperature T greater than 0 Kelvin, then what will happen? You know, in that condition, some of the covalent bonds in this valence band actually get broken and electrons are released. And those electrons actually will move from this valence band to the acceptor level. As you can see, I have marked here that an electron after breaking of a covalent bond moves to the acceptor level, and a very small amount of energy, almost equal to 0.01 electron volt, is needed for this. So when there will be a little change in temperature, little rise in temperature, that is temperature is slightly greater than 0 Kelvin, then it is possible that some of the bonds in this valence band will broken and the electrons will be released, and those electrons will move to the acceptor level. And the atoms present in this acceptor level actually gains that electron, and so they become negatively charged. So I have shown here that the electron moves here, and this is now the atom which will gain it, that will become negatively charged. And in this way, actually a negatively charged ions of the acceptor impurity atom are present in this acceptor level. Okay. And due to this movement of electron from valence band to the conductor to the acceptor level, there will be a hole created in this valence band. Okay. So a hole is created when electron moves from valence band to the acceptor level. Okay, and this electron has been accepted by the impurity atom. Okay. On the other hand, there will be also some thermal excitation, and so that the some of the electron will move from this valence band to the conduction band. As I have shown by this line, you can see that the electron which gets released due to the breaking of covalent bonds, that moves actually to the conduction band. Okay, actually this is called the thermally generated electron, and this thermally generated electron also leaves holes in the valence band. I have marked here, you can see by this circle, this is a hole which is thermally generated. Okay, so you can see, although only one electron, as according to this figure, moves to the conduction band, the another electron moves to the acceptor level. So according to this figure, there are two holes in the valence band, but only one electron in the conduction band. Okay, one electron has been captured by the acceptor impurity atom in the acceptor level. So definitely the concentration of holes in the valence band, which is denoted by symbol P, is much greater than the concentration of the electron in the conduction band. Okay, and actually if you consider that again an electron moves to this acceptor level, then it again leaves behind a hole into the valence band, and here the atom again becomes an ion, negatively charged ions. So the number of holes generated by such a transition is equal to the number of negatively charged ions in the acceptor level. Okay, in the acceptor level. So what will be actually in that condition the total number of holes in this valence band? That will be actually the sum of the number of ions in the acceptor level, that is Na minus, and plus the concentration of electrons in the conduction band. That will be actually equal to P. Okay. So in this way, you can see that the concentration of holes in the valence band is much more greater than the concentration of electron in the conduction band, and so actually the majority charge carrier in this case is in fact the positively charged holes in the valence band, and these holes are actually responsible for the p-type conduction. Okay, so now let us consider that this N represents the electron concentration in conduction band. Actually these electrons, you know, have been moved from the valence band to the conduction band due to the thermal agitation. Okay, and so these are called thermally generated electron, and they leave behind the thermally generated holes in the valence band. And P represents the whole concentration in valence band. Okay, but these holes are created by two means, you have seen. And Na we consider is the total acceptor concentration. This is the total number of acceptor atoms or impurity atoms in the acceptor level. And Na minus, this is actually the ionized acceptor concentration. It means these are the number of atoms which have actually absorbed the electron which moves from the valence band to the acceptor level. So you can see this concentration of holes in the valence band, that will be simply equal to the concentration of electron in conduction band and the concentration of ionized acceptor atoms. okay, or ionized acceptor atoms, or you can say the concentration of negatively charged ions in the acceptor level. I think this fact is clear to you. But as the aim of this semiconductor is to conduct the material only by the due to the doping, not by the thermal agitation. So actually, the number of electron moving from valence band to the acceptor level is much more greater than the number of electron moving from this valence band to the conduction band. And so in this condition, actually the concentration of electron in conduction band and the concentration of ions, acceptor ions in the acceptor level are not equal, but n is much smaller than this Na minus. And if n is much smaller than Na minus, then here you can easily neglect this n, that is concentration of electron in conduction band, with respect to this Na minus. So for a time being, we can say that this P, that is concentration of hole in the valence band, is almost equal to the concentration of ions in the acceptor level. Okay, so P is almost equal to Na minus. First of all, we will find the Fermi level, okay, of this p-type semiconductor. And for this, we will calculate the value of this P, and we will also calculate the value of Na minus. Okay. And after calculating the value of P and Na minus, we will substitute those values in this equation 1, and solving that very equation, you will get the expression for the Fermi level of this material. Okay. Now, how we can actually calculate the value of P and Na minus, you can see now. Okay. For this, let us consider that this F of Ea, this represents the occupation probability of finding acceptor atoms in acceptor level Ea. This is actually the Fermi-Dirac distribution function. And you know, Fermi-Dirac distribution function F of E is simply called the occupation probability. This is actually the measure of the probability of finding the particles in an energy level E. So if you want to find the probability of finding of acceptor atoms in the acceptor level having energy Ea, then according to the expression for Fermi-Dirac distribution function, you can say that this F of Ea is defined like this. This is just the definition of Fermi-Dirac distribution function. This will be equal to 1 over 1 plus e to the power Ea minus Ef over Kt. You know, F of E is equal to 1 over 1 plus e to the power E minus Ef over Kt. Okay. Here at the place of E, I have written Ea because we are going to find the probability of finding the acceptor atoms in this energy level Ea. Okay. But what is actually this F of Ea in accordance with the definition of probability? You can see there are total Na atoms in this acceptor level. Okay. And total number of atoms is Na. And among these Na atoms, some of have been actually get ionized. So let us consider that Na minus atoms get ionized. So the probability of finding of atoms in this energy level Ea, that will be in accordance with definition of probability equal to Na minus divided by Na. Okay. For example, when you say that when we toss a coin and the probability of head is 1 by 2, probability of tail is also 1 by 2. Why? Because event will be maybe 2, but actual event takes place that is equal to 1. So like that, there are total Na atoms, and Na minus has been ionized. So when you will divide this Na minus by Na, you will get this Fermi-Dirac distribution function or this occupation probability. Okay. So Na minus will be given by Na times F of Ea. Okay. And so Na minus will be equal to what? When we will substitute the value of F of Ea, this will be equal to Na divided by 1 plus e to the power Ea minus Ef over Kt. Okay. But actually in this condition, this Ea minus Ef is much more greater than this Kt, even at room temperature. And if Ea minus Ef is greater than Kt, then this exponential will have a positive power. If x is positive, you know Ex is 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. So this e to the power x will be much more greater than 1. So in this condition, this exponential factor is much more greater than 1. And so in denominator, you can neglect this 1 in comparison to the exponential term. And when you will neglect this 1, our result will be what? Then Na minus will be equal to Na divided by this much. So you can write this Na times exponential to the power minus Ea minus Ef divided by Kt. Or you can write it as Na times exponential raised to the power Ef minus Ea over Kt. So in this way, applying the Fermi-Dirac statistics, we have calculated the value of this Na minus, which represents the concentration of ions in acceptor level. Okay. Now actually we will find the value of this P, which represents actually the concentration of holes in the valence band. And for this we will have to think about the idea which we have learned in the calculation of carrier concentration in case of pure semiconductor or intrinsic semiconductor. Okay. So utilizing the idea of carrier concentration in case of intrinsic semiconductor, you can write that this P, which represents the concentration of holes in case of the pure semiconductor, that formula will be directly utilized here. And you have learnt earlier in previous lecture that P is given as Nv times exponential to the power Ev minus Ef over Kt. Can you remember this result? You have already learnt this in the previous lecture, so you can remember it. Okay. Actually here, this Nv is what? This Nv is called effective density of states of holes at the valence band edge. Okay. And this is given by 2 times of 2 pi mh star Kt over h square whole to the power 3 by 2. Actually here this mh star, you know, it is actually the effective mass of hole, and K is Boltzmann constant, T is temperature, and H is Planck's constant. Okay. So P is given like this. Now we have obtained the value of P on the basis of the idea which we have learnt in case of pure semiconductor, and we have also calculated the value of this Na minus utilizing the idea of Fermi-Dirac statistics. Now we will substitute these two values in this equation 1. Okay, and simplifying that result, we will be able to find the Fermi level. Okay, so now use these two equations 2 and 3 in equation 1, and you can see that then P is equal to Na minus in accordance with equation 1, and the value of P is given here. So at the place of P I have written this much, and Na, we have just learned that Na is equal to this much, you can see here, And so we have equated these two values. Okay. Now to find the value of EF, we will have to do some mathematical steps. And for this, let us take the natural logarithm of this equation. So after taking the natural log, you can see we will get log NV plus EV minus EF over KT equal to log NA plus EF minus EA over KT. Okay. Now bring this last term in LHS and this first term in LHS in RHS. So you will get that this will be equal to EV minus EF over KT minus EF minus EA over KT, and that will be equal to log of Na minus log of Nb. Okay. And here you will take the LCM, that will be KT, and so your result will be EV minus EF minus EF plus EA over KT, and that will be equal to log of Na over Nb. Okay. So this is EA plus EV minus 2EF, and that is equal to KT times log of Na over Nv. And so you can see 2EF is given as EA plus EV minus KT times log of Na over Nb. And so EF is given as EA plus EV divided by 2 minus KT over 2 times log of Na over Nb. And this is actually the expression for the Fermi level of or Fermi energy of a p-type semiconductor. Okay. Now after getting this expression for Fermi level, we will see some of the important facts which are hidden in this result. Actually, you have seen that we have made this calculation assuming that temperature is slightly greater than 0K, slightly greater. It means you are talking about a temperature which is moderate. That is, this temperature is neither very small nor very large. Okay. So actually, the result which we have obtained here in this equation A1 for the Fermi energy of a p-type semiconductor, this result holds only at moderate temperature. It means this result will be not valid when you talk about a temperature which is near about 0 Kelvin or at 0 Kelvin temperature. This result will be not valid. And this result will be also not valid when temperature T is very large. It is infinitely large. Then it will be again not valid. But why? Let us see. If you see this result that T is equal to 0 Kelvin, then when a people does not see the result seriously and in a haste he sees or he or she sees that T is 0, so the second term will vanish, and abruptly such a person says that EF will be equal to EA plus EV and divided by 2. But this is wrong, this is not correct, because here this NV is also temperature dependent. So don't think about only this T, because you know NV, as you can see, is given like this, and from this expression for NV you can see this NV is proportional to this T to the power 3 by 2. So when you will take T equal to 0, then again inside this logarithm you will have to take 0 at the place of this NV. So there will be log infinity which is undefined. It is not defined. It means we can't define EF by using this result at 0 Kelvin temperature. So I have told you that this result which we have obtained for the Fermi level of a p-type semiconductor, that is not valid when temperature is 0 Kelvin. Okay, and you cannot say that at 0 Kelvin temperature EF is equal to this much. You can't say. Okay, I think you have clearly now understand this fact. Now again see, when you talk about a very large temperature, that is T is tending towards infinity, then what will happen? You can see when temperature is made very large, then actually there will be a very much thermal excitation, and a large number of covalent bonds in this valence band will be broken, and a large number of electrons will move to the conduction band. So in that condition, this condition will be not valid. That is, then you can't take that this P is much greater than N, because then a large number of electrons will move to the conduction band. Okay, and when this condition will be not valid, then you cannot neglect this N with respect to this Na minus, and so you cannot write that P is almost equal to Na minus. You can't write it, but the result which we have obtained, that is based on this assumption. But at very large temperature, you have seen that this assumption is not valid. Okay, so if this condition is not valid, then this result will be also not valid, because this result has been obtained on the basis of this idea. Okay, so it is clear that the result for the Fermi level, which I have mentioned in this equation A1 for the p-type semiconductor, is neither valid at 0 Kelvin temperature, and it is also not valid at very high temperature. So actually this result is valid only at a temperature which is neither very small nor very large. That is, the temperature is moderate. Then this result will be valid. Okay. Actually, in that condition, you can see this figure. When you talk about a moderate temperature, then this Fermi level you can see from there will lie between the top edge of the valence band and the acceptor level. In actually between these two levels, the Fermi level of p-type semiconductor will lie. Okay. So we simply say that Fermi level at moderate temperature lies near the middle of the acceptor level and the top level of the valence band. Okay. But as you will increase the temperature, then more and more electron will move from valence band to the conduction band, and so that this Fermi level then rises. This rises, and on increasing temperature, finally this Fermi level goes to the position of this intrinsic level. Intrinsic level means this is the Fermi level for the pure semiconductor. If there will be no doping, you are taking the pure semiconductor of germanium or silicon, then you know the Fermi level lies between this top level of the valence band and bottom level of the conduction band, which is actually called intrinsic level. And so on increasing temperature, finally this Fermi level will move up, and finally it will go to the position of this intrinsic level. And if the Fermi level now coincides with the intrinsic level, which is actually equal to Eg divided by 2, where Eg is the band gap of the pure semiconductor. You know, this is actually equal to Ec minus Eb. This Eg is equal to Ec minus Eb. And as the Fermi level coincides at very large temperature with the intrinsic level, so in this condition, our p-type material behaves like an intrinsic semiconductor. Okay. So whenever a question is asked to you that if a p-type material will act like a pure semiconductor? Answer will be yes. This depends on temperature. When temperature has such a value that the Fermi level of a p-type material moves to the position of the Fermi level of pure semiconductor, that is, it coincides with the intrinsic level, then the p-type material will behave like an intrinsic semiconductor. Okay, so this is a very important fact. And so this result which we have obtained, this contains so many important facts, and I have discussed all those facts, and I hope you have understand each and every fact clearly. Okay. Now, after solving the problem of finding expression for Fermi energy for a p-type semiconductor, now we can easily find the concentration of holes in the valence band, because here the majority charge carrier is the positively charged holes. So our aim is to find the concentration of holes in this case, in the case of this p-type material. You have obtained the concentration of electron in conduction band in case of n-type material, but here when you talk about the carrier concentration, that means concentration of holes. And how we can obtain it? For this, let us see this result. This equation 3 actually represents the concentration of hole in this p-type material, okay, in the valence band. And this can be obtained easily because now we have an expression for this EF. So if your aim is to find this P, you will simply put the value of EF which we have just obtained in this equation 3, and then you will get easily the value of P. Okay, so let us see. This is the expression for EF, and we will substitute this value of EF in this expression. You can see P is equal to NV times exponential to the power EV minus EF over KT. And now we will substitute the value of EF here. But before that, I have simplified it. You can see this is equal to NV times e to the power EV over KT times e to the power minus EF over KT. Okay. Now this factor e to the power EV over KT, that is, and now we will put the value of EF, and you have seen that EF is equal to this much. Okay, so let us put it. So this will be e to the power minus EA plus EB over 2 minus KT over 2 log of NA over NV and whole divided by KT. Okay. Now let us simplify it. This factor is at is, you can see, and this second factor can be written as e to the power minus EV divided by 2 KT times e to the power minus EA divided by 2 KT. Okay, and times, now when you will raise this as a power of exponential, then this KT will cancel out. Okay, and this result will be NA over NV to the power half. Here the property of log has been utilized, and you know it that. Okay. Now we will simply multiply all these three exponential terms. Okay, and so after multiplication, you can see this P will be equal to NV times NA by NV whole to the power half times e to the power EV minus EA over 2 KT. Okay. Now here this NV to the power half in denominator will cancel, and your result will be NA times NV whole to the power half times exponential raised to the power minus has been taken as a common factor, and this is EA minus EB over 2 KT. Okay, EA minus EB over 2 KT. Now, when you will substitute the value of this NV, and you know NV is equal to 2 into 2 pi mH star KT over H square whole to the power 3 by 2. So when we will substitute this, what will be our result? Our result will be a square root of 2Na times 2 pi mh star kt over h square whole to the power 3 by 4 and times exponential to the power minus delta E by 2 kt. Here, what is this delta E? You can see this delta E has been written at the place of EA minus EB. You can see this is the value of EB and this is the acceptor level which is EA. And you know the minimum energy needed for an electron moving from this valence band to the acceptor level. What will be that minimum energy? That will be EA minus EB. Okay? And so when this electron will move to this acceptor level, then the atom in this acceptor level will become an ion, negatively charged ion. So this EA minus EB is the measure of the ionization energy of an atom present in the acceptor level. So this is called ionization energy for the acceptor atom. Okay? And this is the expression for the concentration of holes in the valence band in a p-type semiconductor. And you can see from this result that this concentration depends importantly on two factors. First one is the total number of acceptor atoms, Na, and it is proportional to a square root of Na. So as the number of impurity atoms increases, the concentration of holes in valence band in case of p-type semiconductor also increases non-linearly. Okay? And you can also see that this P depends strongly on this temperature T. Okay? Here is T and here is T. So actually for larger temperature this exponential factor dominates over this T, and so we simply say that roughly this P increases almost, here the word almost has been used because T is also present here. Okay, so almost with increase in temperature this P, that is the concentration of holes in valence band, increases with temperature. So the concentration of holes increases non-linearly with the increase in Na, that is number of acceptor atoms or concentration of acceptor atoms, and it also increases almost exponentially with rise in temperature. So in this way we have easily solved the problem of calculation of concentration of holes and the Fermi level in case of a p-type semiconductor. So in this way we have completed our lecture on the calculation of concentration of carrier concentration and the Fermi level in case of both pure semiconductor and extrinsic semiconductor. Okay, and I think after watching all these videos your concept regarding this problem will be very clear. Okay, thank you very much.